Welcome back. So up to this point, our models have dealt with, structured data, list of numbers, basic spreadsheets, but what happens when we want an AI to process an image? How does a computer actually see? Today we are diving into computer vision. We're going to look at why our standard neural networks completely collapse when faced with visual data, and how we fix the problem using convolutional neural networks, or CNNs. So why can't we just feed an image into the multilayer perceptron we built back in two videos ago about? Two massive reasons: scale and geometry. First, let's talk about parameters. A standard 1000 by 1000 pixel color image has three color channels: red, green, and blue. If we flatten that into a single line of inputs, that is 3 million numbers. If we connect that to just one hidden layer with 1000 neurons, we suddenly have 3 billion weights to train for a single layer. Our computer will choke and the model will instantly overfit. Second, MLPs have no concept of local spatial invariance. To an MLP, a pixel at the top left has no special relationship to the pixel right next to it. And worse, if you teach an MLP to recognize a coffee cup in the center of the frame and then move that exact same cup to the corner, the network sees a completely different set of inputs and has no idea what it's looking at. So to solve this, we threw out the idea of connecting every pixel to every neuron. Instead, we're using convolutional layer. The core engine of a conv layer is a filter, some also called a kernel. Think of a filter as a tiny flashlight. Let's say a 3 by 3 pixel grid that scans across an image or across the image. As it hovers over a patch of pixels, it computes a dot product looking for a specific pattern, like a vertical edge or a color contrast. Because we use the exact same filter as we slide across the entire image, we use a technique called parameter sharing. Instead of learning millions of individual weights, we only need to learn the weights of that tiny 3 by 3 filter. Even better, because that filter scans everywhere, it can recognize an edge or a shape regardless of where it appears on the screen. Spatial invariance achieved. Now, as we slide these filters around, we have three levers, to control our output. First is the spatial extent, F, which is simply the size of our filter, usually 3 by 3 or 5 by 5. Second is the stride, S, which dictates how many pixels we jump when sliding the filter. A stride of 1 moves pixel by pixel, a stride of 2 skips every other pixel, shrinking our output. Third is zero padding. If you slide a filter over a grid, the edges get ignored, and the image shrinks over time. To fix this, we pad the outside of our image with a border of zeros so our filters can properly analyze the very edges of the picture. To calculate the exact size of our new output, we use a simple formula. And the formula is right here. Oh, sorry, I forgot to say that P is a zero pad. So where N is our input size, now if your math doesn't result in a clean whole number, your stride is misaligned or your filter won't fit the grid properly. So it has to be a clean whole number. So as our images passes through multiple convolutional layers, we accumulate a lot of feature maps. To keep our computational costs down, we need to aggressively compress this data. We do this using max pooling. So we slide a window, typically 2 by 2, over a grid, and we simply extract the highest single number from each window, throwing away the rest. Why? Because the highest number tells us that a specific feature, like a sharp curve or a bright spot, was strongly detected in that region. We don't care about the exact pixel location anymore, we just care that the feature exists. Finally, after we use our conv layer, compilation layer, and pooling layers to extract and compress all these visual features, We flatten the remaining small grids into a 1D vector and feed it into a standard multilayer perceptron called a fully connected layer to make our final prediction, dark roast, medium roast, or light roast for coffee. And here's some visuals. Here's visual of an input image of to this dog and how it would go through the layers. And at the end, 95% sure this is a dog. And that's the mechanics of convolutional neural networks. We went from billions of tangled wires to small, smart filters that can see spatial patterns anywhere on the screen. In the next video, taking a quick trip through history to look at the legendary CNN architectures that built the modern AI landscape we see today.